the general equation of the form x square y double dash plus x px y dash plus qxy equal to 0. Okay, and then we know we can find p naught, we can find q naught, and then we have seen that we can talk of initial equations of the form r, what was that, r minus 1 plus p naught r plus q naught equal to 0, and this gives us two roots, r equal to r1 and r2. And we have seen that one of the power series can be summation, say, let us write it as um, I can take x to the power r1 common from the summation. So one series will be like this, and the other series can be like this, summation, say, bn xn. I've changed the coefficients now because the two series are going to be different, right? So where n varies from 0 to infinity. Okay. Whereas we take our general solution to be something like this, x n plus r, n varying from 0 to infinity, right? This we had seen. Now, so far so good. I mean, you have also practiced problems, how to find r, how to find the roots of the initial equation, and so on and so forth. The only issue now was, I mean, depending upon the nature of the roots of this initial equation, can we be always sure that we are going to have two series of this kind? Or what about, depending upon R1 and R2, what are going to be the nature of the series solution that we are going to get? Okay, so for this, the theorem that was given by Frobenius, it is still, the theorem is talks of the Frobenius series solution. Okay, now according to this theorem, see, what happens is that we are assuming two things here, that number one, my differential equation is of this form, right, plus qxy equal to 0. Secondly, because we are assuming that x equal to 0 is a regular singular point, that means both p and q are analytic, and we are assuming that my px is actually summation p and xn, where n varies from 0 to infinity, the way we did yesterday. So it's going to be p0 plus p1x plus p2x square and so on, and qx is actually nothing but summation qn x to the power n from 0 to infinity. Why? Because x equal to 0 is a regular singular point, and therefore both small p and small q are analytic at x equal to 0. Now I say let r1 and r2 be the two roots of the initial equation, okay, and we assume that, see, if there are two roots, obviously one has to be greater than the other. So I assume that R1 is greater than or equal to R2. Okay. So that means I am considering the case when the initial equation has two equal roots also, or the repeated roots also. Okay. Now, then this theorem says that the first rule that it says, it talks of the case when x is greater than 0. Okay. Now, why we are talking of x greater than 0? Because even if x is less than 0, we can replace x by mod x and we get the same kind of a result. Okay. So we talk of the case where x is greater than 0. Now, for x greater than 0, the theorem says that the one solution, corresponding to the larger root. Okay, so that means a solution of the form x to the power r1 summation a n x n, n from 0 to infinity. Okay, so for x greater than 0, the theorem says that there exists a solution of this form. Okay, solution kiska? Of this differential equation 1. Okay, so definitely that means one thing is clear from here, that if R1 and R2 are the two roots, then corresponding to the larger root, we definitely have a power series solution of this form. Okay, so this is a Frobenius series. Actually, this series itself is called as a Frobenius series. Okay, so for the larger root, this is definitely going to exist. Okay, the second rule says, now this is important. The second rule says that if R1 minus R2 is neither 0 nor a positive integer. Okay, it's neither 0 nor a positive integer. That means what? R1 minus R2 do not differ by an integer. Okay, and R1 minus R2 is not equal to 0. That means what? R1 is not equal to R2. So if it's neither 0 nor a positive integer, then there exists a solution. For x greater than 0, definitely, another solution of the form x to the power R2 summation bn xn, n from 0 to infinity. Okay, so that means once we have obtained the roots, see, both, one more thing. Of course, this is as far as the existence of the series is concerned. Okay, this means that once we have obtained the roots of the initial equation, which was quadratic in nature, and definitely we had two roots, R1 and R2. That means existence of two roots does not guarantee the existence of two linearly independent power series. Okay, this is very, very important, and I don't know how your practical exams are going to be conducted, but then this is a very common Viva question. If R1 and R2 are the two roots of the initial equation, then this does not guarantee that the differential equation is going to have two linearly independent Frobenius series solution also. One will definitely exist. कौन सी वाली? For corresponding to the larger root. The second may or may not exist. Okay, it will exist in which situation? When these two conditions are satisfied. Where? When R1 minus R2 is neither 0 nor a positive integer. Okay, say for example, you get R1 as 1 and R2 as half. Okay, now this is fine. Your larger root is 1. Fine. So definitely this will exist corresponding to R1 equal to 1. So that means you have a series of the form x summation a n xn. This is one of the series, right? Now I look at R2. This is again, and this is not an integer now, but what is R1 minus R2? 1 minus half, half, which is again not an integer. So that means this condition is satisfied, that R1 minus R2 is not a positive integer. Therefore, I can say that for this particular case, I will have a solution of this form, n from 0 to infinity. But had my roots been 2 and 5, no. Definitely it will exist for 5, but I cannot say for sure that I will have a series of the form x square summation b and xn as well. But I will definitely have a series of the form x to the power 5 summation a and xn. Okay. In fact, in either of these cases, definitely when R1 minus R2 is 0, that means what? R1 is equal to R2. So definitely there is only one power series. But even when R1 minus R2 is a positive integer, then also it may or may not exist. Okay, is this clear? So that means once we have to write down the series, we have to ensure this thing also. Okay, is this clear, or is there any doubt about it? If there is a doubt, please पूछ लो.
हम दोनों ही लीनियरली इंडिपेंडेंट सॉल्यूशंस कब एग्जिस्ट करेंगे फिर?
जब R1 minus R2 is not a positive integer.
Okay.
जैसे 1 और 1/2 के केस में बताया ना मैंने अभी, इस केस में. Okay, let's do one problem. Let's try this. Then maybe you'll get. Say for example, if your differential equation is this 2x square y double dash, do it simultaneously because I'll be needing the answers from you. Minus x square plus 1y equal to 0. We have to solve this differential equation. Okay, so obviously we reduce it in that form, so we get y double dash plus 3x upon 2x square y dash minus x square plus 1 upon 2x square y equal to 0. Now, the moment I look at the denominator, I get that x equal to 0 is a singular point, right? So that means what do I have to verify? Only the fact whether x equal to 0 is a regular singular point or an irregular singular point, okay? So for that, we reduce it in that form, for which we can check. So it's going to be 3 by 2 uh, 3 by 2, yeah, that's it, upon x y dash, okay, minus of, okay, ये 2 नहीं चाहिए ना, so it's x square plus 1 by 2 x square y equal to 0, right? So it's basically plus minus minus, यही है ना, because I have to compare it with the standard equation, okay? Now your px is 3 by 2 and your qx is minus half into x square plus 1. Am I right or wrong? Just correct me if I'm wrong. Now this is a constant polynomial, this is a quadratic polynomial, so both P and Q are analytic at x equal to 0. So therefore we can conclude that x equal to 0 is a regular singular point. Okay. So what do we want? We want P naught and Q naught. So from here we obtain that P naught is 3 by 2 and Q naught is, जब x को 0 put करेंगे तो Q naught is minus half. Right or wrong? Correct me if I am wrong. So your initial equation will be, क्या होगी? R into R minus 1 plus P naught R, and how much was P naught? 3 by 2 R plus Q naught equal to 0. Is that right?
Yes, ma'am.
Now give me
Yes,
the,
ma'am.
yeah. So now what are the two roots of this initial?
Minus 1 and half.
Minus 1 and half. Okay, fine. Now, which one is the larger one?
Half.
Half. So it's always take the larger one as R1. So this implies R1 is half and R2 is minus 1. How much is R1 minus R2?
3 by 2.
3 by
3
2,
by 2.
which is not a positive integer. Okay? That
Yes,
means
ma'am.
That means this differential equation is going to have two independent solutions, linearly independent solutions. So I say let y1 be x to the power half because this corresponds to the larger exponent. So it's going to be an xn, n from 0 to infinity, and y2 will be x to the power minus 1 summation bn xn, n from 0 to infinity. Is this clear?
Yes, ma'am.
Right? Now, instead of solving them simultaneously, I mean, finding the coefficients, what we can do is we can derive a generalized. Now today we are going to solve it also. Till yesterday we had only obtained something like this. When we did the problems also, we just obtained that. What kind of solutions are we going to get? Okay. Now today, since that means now I have to find IAN and I have to find BN also, right? But then ultimately somewhere this both these series, they have come from the general solution of this kind, n plus r, n from 0 to infinity, right? So what we can do is, starting with the generalized form, we can end up with some recurrence relation, and then in that recurrence relation, we can substitute r as half and minus 1, and then consequently get the coefficients for an and bn. Okay, this is how we are going to do the things round. Okay, so basically your y in general was x to the power r summation cn xn n from 0 to infinity. Okay, or the way we had written, which was nothing but cn x to the power n plus r n from 0 to infinity. Now we follow the same procedure. Your y dash is going to be summation n plus r cn x to the power n plus r minus 1, and your y double dash is going to be n plus r minus 1 cn x to the power n plus r minus 2 n from 0 to infinity. Right? Now substitute in your differential equation. Okay. Now, what was your first term of the differential equation? 2x squared y double dash. Okay. So it's going to be 2x squared summation n plus r minus 1 cn. Are you doing it simultaneously? Right?
Yes, ma'am.
Plus 3x y dash. So it's going to be plus 3x summation n plus r cn x to the power n plus r minus 1 n from 0 to infinity. And what was the last term? Minus x square plus 1y, right? So it's going to be summation cn x to the power n plus r n from 0 to infinity equal to 0. Okay. Now we'll, of course, take x inside the summation and split the last term. So we are going to get something like, the first term is going to be summation twice n plus r minus 1 cn x to the power n plus r. यही आएगा ना? Because it was x square.
Yes,
Right?
ma'am.
Plus the next term is going to be summation 3 n plus r cn x to the power n plus r, n from 0 to infinity, right? Then it was minus of x square plus 1. So one term is going to be minus summation cn x to the power n plus r plus 2, right? And then the last one is going to be, it was x square plus 1, yeah. So it's going to be minus summation cn x to the power n plus r, n from 0 to infinity equal to 0. Is that right?
Yes, ma'am.
Yes, ma'am.
ठीक है ना? Now, of course, the first term, the second term, and the third term, they can be combined because, sorry, the first term, the second term, and the fourth term, right? So we'll combine them and we get summation n from 0 to infinity. I have x to the power, in fact, I have c x to the power n plus r cn common, right? Now, what do I have inside? 2 into n plus r minus 1 plus 3n plus r minus 1. Am I right? And the last term is going to be minus summation cn x to the power n plus r plus 2 n from 0 to infinity. Okay?
Yes, ma'am.
इसमें तो कोई गलती नहीं है ना?
No, ma'am. Ma'am.
Can you simplify this bracket? अगर हम n plus r common ले, so what do you get? I mean, the first two terms. Okay, I'm just writing it for you again. It's going to be summation n from 0 to infinity Cn x to the power n plus r. Now, just simplify this. Take n plus r common, so it's 2n plus 2r minus 1 plus 3n plus r. 3r. Are you getting anything? Or just leave it. Doesn't matter. आएगा नहीं कुछ. Our things are not going to be simplified. So we leave it as it is. I was thinking if it gets simplified, then it's going to be plus 3n plus r minus 1. Right. Now look at the last term. Okay. This is n plus r plus 2. Right. So I want to make it n plus r. Okay, because I have x to the power n plus r. I want my series to, x to be starting from that. So what do? We change to n to n minus 2, right? So when you change n to n minus 2, you increase your starting point, right? So it becomes minus summation n from 2 to infinity, right? And it will be simply C n minus 2 x to the power n plus r equal to 0. Is that okay? Now, the first term is starting from 0. Okay, the second series is starting from 2. So what we can do is, we can separate out the two terms. That means we can write this first series expansion separately for n equal to 0 and then for n equal to 1 also. Okay, see what happens when n is 0. It is C0 x to the power r into, n is 0 now, so it's 2r r minus 1 plus 3r minus 1. Is that right? What happens when n is 1? It's C1 x to the power r plus 1 into 2n plus 1 n plus 3n plus 1, right? Plus 3n plus 1 minus 1, right? And then the remaining I can write from 2 to infinity. Okay.
Ma'am?
And
Ma'am, it will be r plus 1.
oh, I'm sorry. Yeah, I'm putting n equal to 0. So it's going to be r plus 1, right, into r, you know? And then 3 into r plus 1. Yeah, that's right. And then summation n from 2 to infinity, I have x to the power n plus r into Cn into this whole term, n plus r minus 1 plus 3n plus r minus 1 minus Cn minus 2 equal to 0. Is that right? बताओ.
Yes, ma'am.
अब देखो. Now each of the terms must be 0. This coefficient should be 0 and this coefficient also should be 0 and this coefficient also should be 0. This is how we move about, right? Now when you for n equal to 0, when you see, you are going to get something like C naught into 2r r minus 1 plus 3r minus 1 equal to 0. यही आएगा ना? But C naught is not 0, so you are going to get 2r square minus 2r plus 3r minus 1 equal to 0. So you're going to get some values of r again from here, right? And if you see, this is same as your initial equation. है कि नहीं है?
Yes, ma'am.
Right? So that means the first expression is going to give us back our initial equation, and that is why our values of r, which were minus 1.5, if we solve this. But look at the coefficient when we are dealing with when n equal to 1. Okay, so what are you getting? From there, what are you getting? C1 into 2r square plus 5r plus 2 equal to 0. If you simplify, are you getting this?
Yes, ma'am.
Right. Now again, we have no condition on C1. We don't know whether C1 is 0 or not. But definitely we have now got product of two terms equal to 0. So one thing is very clear. That means either C1 is 0 or 2r square plus 5r plus 2 is 0. तभी तो product 0 है. Right? Now, this term cannot be 0. Why? Because r is either minus 1 or half. So even for r equal to minus 1, this term is not 0. And r equal to half, so definitely this is not 0. Is this clear? So that means the only option that we have is the fact that C1 is 0. Now, is this clear or not? Now, in fact, from the first expression also, since you have already solved your initial equation, of course, I mean, even if we don't impose any condition on C naught right now, we are getting a product of these two terms equal to 0. I'm sorry. So that means again, either C naught is 0 or this is 0. Now, this was nothing but our initial equation. So definitely this is always 0. And because this is 0, so we can say that C naught is not 0. But in the other case, we have got this kind of a situation where we know for sure that this polynomial in R is not 0 because R cannot take any other value except for minus 1.5. So that means if I'm getting a product of two terms equal to 0, then the only option left with me is the fact that C1 must be 0. Is this clear?
Yes, ma'am.
Right.
Yes,
Now,
ma'am.
Yes,
now,
ma'am.
yeah. So now you can use the last part now. See, we have this relation. Okay. So basically, the relation gives you the fact that your Cn is going to be nothing but Cn minus 2 upon the whole term. I mean, what we had, kya tha wo? I need to see it again. Yeah, this term. What was that? 2 into n plus r into n plus r minus 1, then plus 3n plus r
N
minus
plus minus 1.
1. Right? यही था ना?
Yes, ma'am. Yes, ma'am.
So this is your Cn. And this Cn is there for every n more than or equal to 2. Because you got this from the series expansion where n starts from 2. Okay. So now when you put n equal to 2, you are going to get your C2. And what is your C2? This is going to be C0 upon. Now n is 2. So now n is 2. So it's going to be 2 into r plus 2 into r plus 1 plus 3 r plus 2 minus 1. Okay. Similarly, C3. Now C3 will be in terms of C1, which is 0. So that means C3 is 0. Similarly, I think C5, C7, all odd coefficients will be 0. So what you are going to get will be the terms only for C2, C4, C6, and so on and so forth. Now you can find, now you see your coefficients now are only in terms of R. Okay, so that means when R is half, see, you have two options now, when R is half and when R is -1. So basically, for R equal to half, my Cn will be Cn minus 2 upon, I just have to substitute half here, which is going to be twice of n plus half into n plus half minus 1 plus 3n plus half minus 1. And for r equal to -1, my Cn is going to be Cn minus 2 upon 2 into n minus 1 into n minus 2 plus 3 into n minus 1 minus 1. Okay, so basically that means this is going to give you your A2, A4, A6, and so on and so forth. And this is going to give you B2, B4, B6, and so on and so forth. So now you will have your Y1 as x to the power half summation AN(xn), and your Y2 will be x to the power -1 summation BN(xn). Is this clear? Will you be able to do it? Just find two terms. I mean, they'll be okay. Just find A2, A4, find B2, B4, and then let us see how does the series behave. How does Y1 behave? X to the power half. So it's going to be, everything is going to be in terms of A0 then, right? Similarly, your Y2 will be x to the power -half into B0 and so on and so forth. Just give two terms each. क्या आता है बताओ तो?
Ma'am, A2 is A0 by 14.
A2
For
is
A0 by 14.
like 14. So A2 means it's going to be plus A0 by 14 x square. And what will be A4?
A4 is A2 upon 44.
Which in terms of A0 becomes
A0 upon 616.
616 x to the power 4 and so on and so forth, right? So which means this is x to the power 4 upon 616 and so on and so forth. So this is your first Frobenius series for this solution for this differential equation. Similarly, find B2 and B4. Now R is -1 now. So what will be B2?
Ma'am, B0 by 2.
B0 by 2x square, right?
Yes, ma'am.
And what is B4? आएंगे तो सारे प्लस ही.
B0 by 40. x to the power 4.
Yeah, that's perfect. And so on and so forth. So this means plus x to the power 4 by 40 and so on and so forth. So that means this differential equation had two linearly independent power series solution, which we have obtained by this method. So, I mean, had we stopped at the fact that because x equal to 0 is a singular point, therefore power series solution does not exist, we would not have been able to find it. So it is like an option, a step forward, I mean, one step ahead, that yes, if it is an ordinary point, definitely we have power series solution of the form Cn xn. But if it is a regular singular point, then we have power series solution of the form Cn x to the power n plus r. So it's just that r, which is an extra term here, so we need to impose conditions there that depending upon r, what kind of solutions are we going to get. So that is why this series that we have obtained, the series solution that we have obtained is called as a Frobenius series solution. Okay, and this method actually helped us to find a power series solution for Bessel's equation. See, we had seen that the Bessel's differential equation is an equation of this form: xy dash plus x square minus n square y equal to 0. Okay, so this differential equation is called as the Bessel's differential equation of order n. Okay, see, the easiest one is, let us consider the Bessel's differential equation of, say, order 0. So it's going to be of the form x square y double dash plus xy dash plus x square y equal to 0. This is the Bessel's differential equation of order 0 because your n is 0 here, right? Now, let us find the solution for this. It's going to be y double dash plus 1 by x y dash plus y equal to 0. यही हो गया ना? Which, of course, x equal to 0 is the singular point here that we had seen earlier also. So I rewrite as 1 by x y dash plus x square by x square y equal to 0. So this gives me the fact that px is 1 and qx is x square. Okay, so definitely both are polynomials. So definitely x equal to 0 is a regular singular point. I'm writing a RSP for a regular singular point. Okay, now if x equal to 0 is a regular singular point, that means I need to find the roots of the initial equation. And from here, it's clear that your P naught is 1 and Q naught is 0. So your initial equation is going to be R minus 1 plus R plus 0 equal to 0. Right? So what do you get from here?
R square 0.
R square is equal to 0. That means R is 0 and 0. See, now, mind you, it has repeated roots. Right? R1 is also 0 and R2 is also 0. So we are sure of only one Frobenius series solution for this particular differential equation. So it is going to be definitely of the form x to, of course, we are starting with summation Cn x to the power n plus r, n from 0 to infinity. Right? But which we have been writing like this. And since r is 0, so it's going to be something of this form only. Okay, so what I would suggest you is that now, since this is simpler because we are going to have only one, we don't need two values of r. So you can simply start like this only, and the way we have proceeded earlier, just find the solution. I mean, find the coefficients, Cn's. So this is your homework. Okay.